When designing a panel for installation in a non-hazardous area that serves part of a hazardous area, specific requirements apply to the grounding of cable shields, particularly for 4 to 20 mA analog signals. The National Electrical Code, or NEC, addresses these scenarios, especially when intrinsically safe circuits are involved. If the installation was entirely in a non-hazardous area, the standard practice would be to ground one end of the 4 to 20 mA analog cable shield to reduce noise. However, the situation changes when transmitters are located in a Class 1 Division 2 area and intrinsically safe barriers, or ISPs, are mounted in the panel outside the hazardous location. NEC 504.50 typically mandates grounding the shield, but an exception exists when the shield is part of an intrinsically safe circuit. In this context, the question arises what to do with the shield on the hazardous side of the ISB. NEC 504.50 states requirements for grounding cable shields. However, there is an important exception that applies when the shield is part of an intrinsically safe circuit. The exception to NEC 504.50 explicitly states that the shield of a cable that is part of an intrinsically safe circuit shall not be grounded. This is crucial because in the described scenario, the shield on the hazardous side of the ISB is indeed part of an intrinsically safe circuit. Therefore, it does not need to be grounded. The primary reason for this exception is that grounding the shield in an intrinsically safe circuit can compromise the safety of the system. Intrinsically safe circuits are designed to limit the energy available in the hazardous area to a level that is below what is required to cause ignition. Grounding the shield can introduce a path for fault currents, potentially increasing the energy in the hazardous area and negating the safety benefits of the intrinsically safe design. However, the lack of grounding might raise concerns about noise interference. If noise issues arise, several troubleshooting steps can be taken. Firstly, ensure that the ISB is properly installed and configured. A correct setup is fundamental to the proper functioning of the ISB and its ability to isolate the intrinsically safe circuit from non-intrinsically safe circuits. Secondly, use a shielded cable with a low capacitance to reduce noise pickup. The cable shielding effectiveness and low capacitance are crucial in minimizing the amount of external noise that can couple into the signal. Cable selection is important for maintaining signal integrity. Thirdly, consider installing the cable in a conduit or other shielded enclosure to minimize external noise interference. Physical barriers can provide additional protection against electromagnetic interference, or ME, and radio frequency interference, or RFI. Fourthly, use a noise filter on the signal input of the ISB. Noise filters can attenuate unwanted frequencies, improving the signal-to-noise ratio. If the noise issue persists despite these measures, it may be necessary to consult with the manufacturer of the ISB or other qualified personnel for further assistance. Complex noise problems can sometimes require specialized knowledge and equipment to diagnose and resolve. When dealing with intrinsically safe circuits in hazardous areas, adhering to the NEC and understanding the specific requirements and exceptions is critical. In this specific instance, the exception to NEC 504.50 allows not grounding the shield on the hazardous side of the ISB, preserving the integrity of the intrinsically safe circuit. Noise reduction strategies can be implemented to address any potential interference issues, ensuring the reliable operation of the instrumentation system. To further elaborate on intrinsically safe circuits and their application in hazardous locations, it is important to understand the underlying principles and design considerations that ensure safety and reliability. Intrinsically safe, or IS, circuits are designed to prevent ignition in hazardous atmospheres by limiting the amount of electrical and thermal energy available. This is achieved through a combination of circuit design, component selection, and system installation practices. The goal is to ensure that even under fault conditions, the energy released in the hazardous area is insufficient to ignite flammable gases, vapors, or dusts. The design of intrinsically safe circuits typically involves the use of intrinsically safe barriers, or ISPs, which are devices that limit voltage and current to safe levels. These barriers are often installed in the non-hazardous area and connected to field devices in the hazardous area. They provide a critical interface between the safe and hazardous zones, ensuring that energy levels remain within acceptable limits. When selecting components for intrinsically safe circuits, it is essential to choose devices that are certified for use in hazardous locations. These components are designed and tested to meet stringent safety standards, ensuring that they do not generate excessive heat or sparks that could cause ignition. Additionally, the wiring and cabling used in intrinsically safe circuits must be carefully selected and installed to minimize the risk of faults. Shielded cables are commonly used to reduce noise and interference, but as previously discussed, the grounding of the shield must be carefully considered to avoid compromising the safety of the circuit. One of the key aspects of intrinsically safe circuit design is the concept of entity parameters. Entity parameters define the maximum voltage, current, and power that a device can safely handle. These parameters are used to ensure that the combination of devices in an intrinsically safe circuit does not exceed the safe limits. The entity concept allows for the interconnection of different intrinsically safe devices, provided that the overall circuit parameters remain within the acceptable range. When designing and installing intrinsically safe circuits, it is crucial to follow the guidelines and recommendations provided in the NEC and other relevant standards. These standards provide detailed requirements for component selection, wiring practices, and system installation. Compliance with these standards is essential for ensuring the safety and reliability of the intrinsically safe system. In addition to the NEC, other standards, such as those issued by the International Electrotechnical Commission, or EIC, and the European Committee for Electrotechnical Standardization, or CENELEC, may also be relevant depending on the location and application. These standards provide similar guidance on the design and installation of intrinsically safe circuits, and compliance with these standards may be required for certain installations. The proper installation and maintenance of intrinsically safe systems are also critical for ensuring their continued safety and reliability. Regular inspections and testing should be conducted to verify that the system is functioning correctly and that all components are in good working order. Any faults or deviations from the original design should be promptly addressed to prevent potential safety hazards. The documentation of intrinsically safe systems is also important for maintaining their integrity over time. Detailed records of the system design, component selection, and installation practices should be kept to facilitate future maintenance and troubleshooting. This documentation should be readily available to qualified personnel who are responsible for the upkeep of the system. In summary, the design and installation of intrinsically safe circuits in hazardous locations require careful attention to detail and a thorough understanding of the applicable standards and regulations. By following these guidelines and best practices, it is possible to create safe and reliable instrumentation systems that can operate effectively in challenging environments. It is important to remember that the primary goal of intrinsically safe design is to prevent ignition in hazardous atmospheres, and all design and installation decisions should be made with this objective in mind. The following information will delve into the practical aspects of implementing noise reduction techniques in intrinsically safe systems. Noise can be a significant concern in instrumentation and control systems, as it can interfere with the accurate measurement and control of process variables. In intrinsically safe systems, noise reduction is particularly important, as excessive noise can potentially compromise the safety of the circuit. Several techniques can be used to minimize noise in intrinsically safe systems. As mentioned previously, the use of shielded cables is a common and effective method for reducing noise pickup. Shielded cables consist of one or more conductors surrounded by a conductive shield, which is typically made of copper or aluminum. The shield acts as a barrier to electromagnetic interference, preventing external noise from coupling into the signal conductors. When using shielded cables in intrinsically safe systems, it is important to properly terminate the shield. In general, the shield should be grounded at one end only, typically at the control panel or power supply. Grounding the shield at both ends can create a ground loop, which can actually increase noise levels. The choice of cable type can also have a significant impact on noise performance. Cables with low capacitance are generally preferred, as they tend to be less susceptible to noise pickup. Additionally, cables with trusted pairs can help to reduce common mode noise. Twisted pairs consist of two conductors that are twisted together, which helps to cancel out noise signals that are common to both conductors. In addition to cable selection and shielding, proper grounding practices are essential for minimizing noise in intrinsically safe systems. Ground loops can be a major source of noise, so it is important to avoid creating them. Ground loops occur when there are multiple ground connections between different parts of the system, which can create a circulating current that generates noise. To avoid ground loops, it is important to use a single point grounding scheme, where all ground connections are made to a common ground point. This helps to ensure that there are no circulating currents that can generate noise. Another important noise reduction technique is the use of filters. Filters can be used to attenuate unwanted frequencies, improving the signal-to-noise ratio. Various types of filters are available, including low-pass filters, high-pass filters, and band-pass filters. The choice of filter type depends on the specific noise characteristics of the system. For example, a low-pass filter can be used to attenuate high-frequency noise, while a high-pass filter can be used to attenuate low-frequency noise. Filters can be installed at various points in the system, such as at the input of the ISP or at the input of the control system. When selecting filters for use in intrinsically safe systems, it is important to choose devices that are certified for use in hazardous locations. These filters are designed and tested to meet stringent safety standards, ensuring that they do not generate excessive heat or sparks that could cause ignition. In some cases, it may be necessary to use isolation techniques to reduce noise in intrinsically safe systems. Isolation involves physically separating different parts of the system to prevent noise from propagating from one part to another. Isolation can be achieved through the use of transformers, optocouplers, or other isolation devices. Transformers provide galvanic isolation, which means that there is no direct electrical connection between the primary and secondary windings. This can be effective in preventing ground loops and reducing common mode noise. Optocouplers use light to transmit signals between different parts of the system, providing a high degree of isolation. Optocouplers can be effective in reducing both common mode and differential mode noise. When implementing noise reduction techniques in intrinsically safe systems, it is important to carefully consider the potential impact on the safety of the circuit. Any changes to the system should be thoroughly evaluated to ensure that they do not compromise the intrinsically safe design. It is also important to document all changes to the system and to maintain accurate records of the system configuration. In conclusion, noise reduction is an important consideration in the design and installation of intrinsically safe systems. By using a combination of shielding, grounding, filtering, and isolation techniques, it is possible to minimize noise and ensure the accurate and reliable operation of the system. However, it is important to carefully consider the potential impact on the safety of the circuit and to follow all applicable standards and regulations. The following points will further discuss troubleshooting noise issues in intrinsically safe systems. When experiencing most problems in intrinsically safe systems, it is essential to have a systematic approach to troubleshooting. This involves identifying the source of the noise, determining the cause, and implementing corrective actions. The first step in troubleshooting noise issues is to gather information about the problem. This includes noting the type of noise, the frequency of the noise, and the conditions under which the noise occurs. It is also helpful to gather information about the system configuration, including the types of devices used, the wiring practices, and the grounding scheme. Once the information has been gathered, the next step is to identify the source of the noise. This can be done by systematically disconnecting different parts of the system and observing the effect on the noise level. For example, if the noise disappears when a particular device is disconnected, then that device is likely the source of the noise. Another technique for identifying the source of the noise is to use a spectrum analyzer. A spectrum analyzer is a test instrument that displays the frequency components of a signal. By using a spectrum analyzer, it is possible to identify the frequencies at which the noise is most prominent. Once the source of the noise has been identified, the next step is to determine the cause of the noise. There are many potential causes of noise in intrinsically safe systems, including electromagnetic interference, or ME, radio frequency interference or RFI, ground loops, and component failures. EMI can be caused by external sources, such as radio transmitters, cell phones, or industrial equipment. RFI can be caused by nearby radio frequency sources, such as radio stations or radar installations. Ground loops can be caused by multiple ground connections between different parts of the system. Component failures can cause noise due to faulty components or damaged wiring. Once the cause of the noise has been determined, the next step is to implement corrective actions. The specific corrective actions that are required will depend on the cause of the noise. For example, if the noise is caused by EMI, then shielding the cable or relocating the equipment may be necessary. If the noise is caused by RFI, then filtering the signal or relocating the equipment may be necessary. If the noise is caused by ground loops, then implementing a single-point grounding scheme may be necessary. If the noise is caused by component failures, then replacing the faulty components or repairing the damaged wiring may be necessary. After implementing corrective actions, it is important to verify that the noise problem has been resolved. This can be done by monitoring the signal level and observing the effect of the corrective actions on the noise level. If the noise problem persists, then additional troubleshooting may be necessary. In some cases, it may be necessary to consult with a qualified technician or engineer to diagnose and resolve complex noise problems. A qualified technician or engineer will have the knowledge and experience to identify the source of the noise, determine the cause, and implement effective corrective actions. They will also have access to specialized test equipment that can be used to diagnose noise problems. In addition to the troubleshooting techniques described above, there are several other tips that can be helpful in resolving noise problems in intrinsically safe systems. Firstly, ensure that all connections are clean and tight. Loose or corroded connections can be a source of noise. Secondly, use high-quality cables and connectors. Cheap cables and connectors can be more susceptible to noise. Thirdly, avoid running cables near sources of noise, such as power lines or motors. Fourthly, use surge protection devices to protect against voltage spikes. Voltage spikes can damage equipment and cause noise. Fifthly, keep the system clean and dry. Dirt and moisture can cause corrosion and noise. In conclusion, troubleshooting noise issues in intrinsically safe systems requires a systematic approach and a thorough understanding of the potential causes of noise. By following the steps outlined above and by implementing effective corrective actions, it is possible to resolve noise problems and ensure the accurate and reliable operation of the system. When dealing with complex noise problems, it may be necessary to consult with a qualified technician or engineer.